So my next talk is ultra-low latency with Java and terabytes of data. And this sounds really as a contradiction in terms. Ultra-low latency, Java, and terabytes of data. Is that really possible to do? My name is Per, and it's great to be back in Sweden again. I lived in California for 3 years, and being back to my home time, I was born here an undisclosed number of years ago, many more cycles ago, and I did a lot of speak internationally, over 50 talks. I've written a book called Modern Java, been writing for Oracle Java Magazine, Dean Zone, and many other forums. I was one of the starters with Speedment, and well, we go back and forth between Gothenburg and Silicon Valley. I'm going to talk about this in this presentation. How many of you guys have put in a progress bar in your code? Well, quite a few of you. I don't want to talk about that. I want to talk about the opposite, how you can make your application snappy and speedy. So I'm going to talk about ultra-low latency. And since this is my talk, I get to decide what ultra-low latency is. So in this presentation, ultra-low latency is 200 nanoseconds. And just to give you some reference, the time it takes for light to travel in the width of my laptop is about 1 nanosecond. So about 100 nanoseconds is to the clock there and back again. And that is also the time it takes to pull in 64 bits of memory from main memory into the CPU. So this is actually then just 2 such fetches. Is that possible? Let's see. And why is this even necessary? Who cares about 200 nanoseconds? I can't see that with my eyes anyway. The problem is that you might have a microservice architecture with a lot of microservices, or you might have a huge number of computational steps that has to be invoked to yield the actual end result. Maybe you have 1 million invocations. And then of course, it depends. The total length depends of the parts, of course. So it can be very important. So why are applications slow? There are many reasons to that. One reason is, of course, slow databases. Data might be on several nodes and no affinity across node data. I will tell you a little bit more what affinity is. Data is remote in some sense. Maybe you have unnecessary object creation or garbage collector problems. And you might have a lack of parallelism in your application. Let's start with databases. That's quite quick. We all know that databases are slow, and we know that they have more and more data. And even the fact that they are located on another server makes them not ultra-low latency. So let's not spend so much time there. So let's go into several nodes and no affinity across data. Let's say you have data that has no affinity. And I will tell you a little bit later exactly what affinity is. But it's roughly that things can be divided in a good way. So suppose you can't divide them in a good way, then you have low affinity. The problem is then you can't have low affinity, low latency, and scale out at the same time. They are mutually exclusive. So you can have low affinity and scale out, but then you don't have low latency. Or you can have low affinity data and low latency, but then you can't scale out. So that is the problem. And why is that? So let's see this picture. Let's say that squares are trousers and triangles are shirts, for example. And blue things are male and red stuff are for women. So that's really good. If we want to compute something regarding men, we can do that on node N1. And we want to compute something about women stuff, we can do it on N2. In this case, data is affinity. They have a high degree of affinity between data because we know how to pair them together. And that's good. But next year, disaster strikes. There is a unisex fashion. So you don't know what kind of shirts are being used in this case. So you have no clue. So you have to put all the shirts on both nodes, for example. And there goes your scale out, because now it's scale up. And maybe a triangle is not just one shirt or one pair of wearable thing. It might represent 1 million or 1 billion of those. But then, of course, we can just have a few of them on one node and a few on another node. But then, of course, if I want to reference them, I need to grab them over the network. And there goes my low latency. So this really shows the essence of the problem. And in this case, first example, we only have 2 different products and 2 different affinity classes, so to speak. What if we have 8 different objects and 8 affinity classes and 8 nodes? Or what if we have 1,000 different objects and 1,000 affinity groups and 1,000 nodes? Well, I have an illustration how to solve this. It looks like this. It doesn't work. So you can't have this at the same time. Okay, let's go to the other point. Data is remote. And we are lucky these days because the performance of computer goes up every year. But no one has come up with a solution for the speed of light. It's been unchanged since Einstein made a statement that the speed of light is constant. So that is a problem. So if I have data in New York and want to access data in San Francisco, for example, we will have a latency round trip of about 45 milliseconds, which is way too slow. And it doesn't matter if it's Stockholm or Gothenburg or whatever, it's too slow anyway. So let's see if we have 2 computers, we have maybe 2 Linux boxes, and we connect them through a dedicated switch. Then we come down to maybe 100 microseconds, which is fast, but still way too slow for being ultra-low latency. So let's go to the extreme and just connect 2 boxes with a twisted cable. And if we can use some kind of busy waiting and we can do process CPU affinity and a lot of black belt technologies, we can come down to 25 maybe microseconds. But that's still 2 orders of magnitude too slow. So this is not a way forward to ultra-low latency. So maybe we can have them within the operating system of the machine itself. Well, it turns out that the context switch from one process to another will set you back maybe a microsecond. And it will also ruin all the caches and everything in the CPU, so you will run slow for a while. So this is not really a solution. So next step is unnecessary object creation. I think this is the third lowest amount of information you can have on a slide. It's 2 characters. You can, of course, have 1 character and no character at all, which can be powerful in some presentations. But this is 1 second. And what is 1 second? 1 second is an example of a garbage collect, stop the world, of course. And that's way too much than ultra-low latency. So again, this guy shows up, the slow garbage collector. We don't want to see him. And of course, as I told you in my previous presentation, the problem is that when we create a lot of objects on the heap, we will undoubtedly have a garbage collect problem. And that will kind of, in some situation, prevent our application from being ultra-low latency. Okay. I also told you in the last presentation that many extra objects are created when you do a map. Each of those objects are subject to overhead and byte alignment. They live for a long time and have to be evaluated by the garbage collector. And it's difficult to retrieve objects because in this case we only have key values, so we have to have tree maps, and all those things add up and gives you a tremendous garbage collect problem. So just writing a single object in main memory takes 200 nanoseconds. This is the smallest Java object I can come up with. And when you write that to main memory, it takes about 200 nanoseconds. And that's all my budget I have. So the conclusion is creating shared objects is not ultra-low latency. So this means that you have to be super careful what you do if you want to write low latency applications. Another problem is lack of parallelism. So maybe you've seen you have 32 CPUs, but when you see what your Java process is doing, it's consuming 100%, but all of your other 31 CPUs are not really used. So I guess this is I've seen this many times. So the solution is In-JVM-Memory, and what is that? In-JVM-Memory is different from just in-memory. So in-memory, of course, you have data in RAM, and the application is remote in some sense, maybe connected to a grid or other machine or in another process. Whereas in JVM-memory is the same, but the application resides within the JVM. You can actually address the data within the JVM. So if we look into the details here, this is a picture of the die in an Intel CPU. And as you can see, or you might see, it has 8 CPU cores. This is what you see here. 1, 2, 3, 4, 5, 6, 7, 8. And we have memory and I/O drivers on the side and power supply. And here you have the actual logic of the CPU at the top and at the bottom. And the further to the middle you get, the more caches you get. So this is the L1, L2, and this is the shared L3 cache. And the good thing is that caches, they have much lower latency than main memory. So if you're lucky and can grab your data in the L1 cache, it's 0.5 nanoseconds. L2 is 7 nanoseconds and L3 is 20 nanoseconds. Whereas 64 memory read is 100 nanoseconds. It's much more expensive. And it's likely that the more modern processors you have, you might be able to improve this, but this is much harder to improve because now we're penalized by the speed of light. That can't be really scaled. So in example here, we have latency performance between an In-JVM-Memory solution and a grid of 4 nodes. And it's a big difference because as soon as you get out on the net, you will lose a lot of time. Okay, that sounds good, but how do we scale? Is that even possible? Well, one good thing is that I think it was 2 years ago, a gigabyte of RAM for the first time in the human history cost less than a cup of coffee on Starbucks. So that's good. It's cheap. But is it scalable? Well, today you can get up to 12 terabytes of data if you use 4 of those guys up there. And you can also buy them on AWS. So, and I have reason to believe that soon you can scale up to 48 terabytes in the next generation of CPUs. So scaling up is quite simple. You just select another server. Simple. And that must be super expensive, at least what I thought, and many of my partners thought. So we investigated the correlation between memory sizes and cost. And actually, it's a complete linear cost. For example, X1E NX large. It's completely a linear scale of how much memory you have. I thought, and many with me, that it was like this, but it was completely linear. Okay, what if we have more than 12 terabytes? How many of you guys work with data more than 12 terabytes today? One person. Interesting. I don't do that, but that's good. Then there are some tricks. Of course, if you can shard your data, of course, if you have different regions, that's kind of a cheating way to get around the 12 terabyte limitation. You can do memory mapping. Intel, for example, has an SSD, which is very quick, that sits actually on the memory bus and emulates memory. And of course, it will make access slower, but it's quite efficient anyhow. So you can go up to maybe 32 terabytes or something with a little bit performance loss, but not that much. Or maybe you have 12 terabytes, but you don't have to have 12 terabytes to solve the problem at hand. Also, what if my data grows? Well, I can almost promise that if it fits today, it will fit tomorrow, because there is an exponential growth of memory capacity. So unless your data grows even more than the exponential growth of memory, it isn't really a problem. And still, the performance is vastly superior over sharding over distributed nodes if your data is low affinity. Okay, so recap: low affinity, low latency, scale out doesn't work, but In-JVM-Memory makes it work, but then it's scale up. Okay, so let's go to what I do with Speedment. We have, of course, a solution with this, and I already showed this video, so let's skip that. So it's the in-memory DataStore, so it will create snapshots of the data source and place it in the JVM in a clever way. And all the data is off-heap, and all the indexes are also off-heap. And all the operations, for example, finding something bigger than something or in a set, so operations like that are performant regardless of how much data you have. And it has no impact on garbage collection. It doesn't matter if we have a megabyte or a terabyte or 10 terabytes. It's the same garbage collection, basically. So you will end up with a much smaller heap and more efficient store off heap than on heap. And of course, you use streams to access your data, and a stream is just an interface. And this is something I wrote an article on in Oracle Java magazine I think 2 years ago now. So we have this construct with streams that is kind of declarative, as I explained in my previous presentation. SQL is declarative in the sense that it says what you want to have, but not how the database really executes the query. The same is true with streams. So in this example, the stream is free to pick up an off-heap index and really retrieve all the film ratings that are PG-13 without really iterating over any objects. So this is an example. Just counting them is actually very simple because the index knows how many items are in each bucket. So in this case, what we're saying is really use the index rating and see how many objects are in that bucket, and that will complete very quickly. You can also do more advanced things. So in this example, we collect it to something called a JSON aggregator, which also lives off-heap. And the cool thing with this is that we never materialize any film objects. So the stream itself will detect that this is something that can be done off-heap. And if we look into the details, it will see that I will use the rating index, which is illustrated here. And these are actually addresses within the memory. So it will directly go to the index corresponding to PB13 and point out which elements or which films are PG-13. And then it can extract length and title off-heap and put it in the accumulator, which is also off-heap. So it's kind of, it's able to decompose its old stream and apply the primitive operations directly off-heap without creating a single Java object. So we're reasoning about Java objects, but they never exist in reality. It's kind of a magic thing. And so on. Okay, where you can also create joins. So you can join tables that lives off-heap. In this case, we join language and film. So we get language data and which film, what they're talking. We can do off-heap aggregation. So we can build up aggregation. In this case, we aggregate with a key on language and rating. And then we compute the average length for each of those buckets. And this operation will be performed completely off-heap. And they can be also, all the aggregators can be used in combination with joins. And they, of course, can be parallel too. So if we have parallel operations, we will have, if we have 8 cores, we will have 8 off-heap aggregators that will run on each thread. And once they are completed, all the accumulators will combine to one. And so we will have a speed up of approximately linear to the number of CPUs we have. So then we don't have this problem. Then we will be able to use all the CPUs in the machine. So let's look at the hands-on demo. I have in this example the Sakila example database, which is actually about films. You can download that, or there is a Docker instance available if you want to try it out for yourself. And I will run this benchmark shown here, which is what I've shown several times. I have the film, filter out rating equals PD13, and I count the occurrences of those. And I will take a snapshot of the database, which I have in my JVM, and run that. I haven't done any specific trimming here. I just went to this website, used the Initializer, and downloaded on my computer. So I connected to the database, I generated the domain model, and now we are at the demo. So it's here. Okay, and before I speak, I should start it in the background. So now it's running. So this is a JMH test benchmark. And you can see what's going on here. I have two streams that you see here on the screen. One short, called filter and count, and one more complicated, complex one, which takes all the films, sorts it in length descending order, skip the first 745, then takes the next 5, extract an integer from the film rental duration, and computes summary statistics on that integer. Now, summary statistic is a standard stream operation. And this shows how this clicks into the entire stream infrastructure. So you can use anything on a regular stream with these streams. So now it's running here in the background. And as you can see with JMH, it's running a warm-up first, and then it runs the actual benchmark. And because we need to allow the JVM to warm up, it will take some time to run the actual benchmark. But now we're ready. So let's see here. We got the more simple one, filter and count. We got 5 million, almost 6 million operations per second. And the more complex, we've got 1.5 million operations per second. And if you calculate, invert 5 million, you get 200 nanoseconds. And it's because it's more than 5 million, it's less than 200 nanoseconds. So that shows that really possible to do ultra-low latency with Java streams on off-heap memory. So that's really cool. Now an even cooler thing is to use, oops, it's difficult to see. No. I've used Java 8. Let's use Grail VM here and rerun the test. So this is the new kind of C2 compiler that's out there in Grail VM. And this will make a big difference when you're using Stream because it's able to do escape analysis much better. So now we're running a new test, exactly the same test, but with another JVM. And that will take a while. Now you can see here, for example, that we it took about 2 seconds to load the entire database off-heap memory. And we loaded about 50,000 entities. And you can see how much data and index they occupied in total here. And now we run the second test. So now it's the warm-up. We load the data. Let's see, well, you can set a lot of options also when you do this test. You can use more threads. I only use one thread because the granularity of my timers on the Mac computer doesn't allow me to measure nanoseconds. So I do this trick and I measure just one thread throughput and then invert the value. So now we do 14 million, and that's astonishing. It's an astonishing performance on a laptop computer. And even this more advanced operation with sorting and skipping and everything, I can do almost 3 million of those per second on a laptop computer with one thread. So that's good. So if we look at it like this and run it over several JDKs, we have this kind of performance. I said 200 nanoseconds was the goal, but with Grail VM we can come down to almost 50 nanoseconds, which is half the time it takes to load just 64 bits from main memory. I think that's good. So I think this technology is very interesting. Of course, since it's Java, you can use it on any database that you can connect. Everything actually that can be converted to a stream can be used in this way, even Google Sheets. You can deploy it on any cloud, like Oracle Cloud or Google Cloud or whatever. And you can use it with the IDEs because it's just generated Java classes. And deploy it with any web server, Spring or J2E, whatever. I don't know what you use, but most of it is covered. So that was a little bit shorter presentation. So I open up for questions. Of course, I have a Swedish slide, but let's hear a question first. Yes?
So is there not a risk that your debugging will end up being you looking in a hex editor or something on your off-heap memory?
The way it's laid out in memory, of course, it's like you said, it's laid out kind of in a hexadecimal form. So eventually you will hit that kind of byte buffer that contains actual data. But you can see the serializers that's being generated kind of reveals how data is stored. So you can actually trace them and see what's going on and see which bit is accessed. And you can even modify them if you're not happy with how they work. Oh, okay. Another question? Yes? Good question. There could be. In the beginning, that was the case. But in the end, we realized that the indexes were very low cost. So we actually create indexes for every column because they're so low cost. But in the beginning, we did that, exactly what you said. Okay, more questions before the Swedish slide? Okay. What if I have a transactional application? I talked about snapshots. But if we have a lot of transaction going on, of course, this way of doing things is much better for analytics kind of application than transactional. So if you have thousands of queries per second that updates your data or update operations, this is not a good fit. But of course, you can argue that if you have a query that takes 10 minutes and just taking a snapshot takes 1 minute and then you get the query immediately, that might be better. And the snapshots are really consistent with the database, so it's an eventually consistent view of the database. How can I pin down my application to a specific CPU? Of course, it's important that you have different CPUs. You want to run your application on a specific CPU in order to improve your performance. And in Java, you can't do thread set CPU affinity. But if you deploy them with Docker, for example, you can actually pin down your application to a specific CPU if you want to have really good single thread performance. How does memory management work off-heap? A little bit related to your question. We have written our own memory manager, actually. So it's tricky. But it's doable. And it's kind of C-like, so you use kind of malloc and structures, stuff like that. I have data in a NoSQL database on file. As I said, anything that can be converted to a Java stream can be imported into data here. So it can be a CSV file, Avro file, or whatever file. How does the snapshot affect the application startup? What if I had trillions of rows? Doesn't take a long time to start my application. Yes, it does. I think you can load maybe 2 or 3 million rows per second on a server-grade computer. But then again, if you have billions of record, it will take some time to load. So in those scenarios, you have to have several nodes, redundant nodes. So while taking down one node for maintenance or upgrade, you have to have other nodes up and running. If I stream over a gazillion objects, won't my heap overflow? Because if I have a lot of objects and I just use them as normal objects in my Java, I will still create a Java heap problem. Isn't that the case? And the answer is, of course, yes. If you're not careful what you do and start to create a lot of Java objects, you will eventually have garbage collection problems. And that's precisely the reason why we did all those off-heap aggregators and off-heap JSON collectors and stuff like that. So we don't have to create actual Java objects. And actually, you can create your own off-heap structures with a little bit of work with this tool. Does Speedment rely on C, C++ libraries or native code? No, it doesn't. It doesn't even depend on unsafe. It's just byte buffers. That means that you can deploy this from a supercomputer down to a Raspberry Pi or a watch or a mobile phone. Okay. Thank you so much for all the questions. Thanks.